Okay, I want to go through several examples with you to show you how to solve problems using the kinematic equations. So I came up with a 5-step process, and I recommend that you go through this every time you have a kinematics problem. So here's how it works. Well, the first step in the process is that you need to identify that it is in fact a kinematics problem. And right now, in week 2 or 3 in this class, it will be a kinematics problem. Later on, as we learn more techniques in physics, you'll have to be able to recognize when the kinematic equations are the right tools for the job. This will come with experience. You'll be able to do it when the time comes. For now, you don't really have to do step 1 because I'm just telling you it's kinematics. Okay, step 2, identify your known quantities. So you read the problem and write down what information you are given. Step 3, identify unknown quantities. Generally, this is what the problem's asking you to solve for. Step 4, you then consult your list of kinematic equations and pick the right one for the job. Sometimes there will be more than one equation that will work, and you can just pick the one that will be easiest to use, where you have to do the least amount of math. So step 5, solve for your unknown quantities. You might have to do some algebra. In some cases, you might have to use the quadratic formula. We'll get to that in the next video. So let me show you how this works by going through 3 examples. They're all pretty simple. We will deal with some pretty intricate kinematics problems, especially when we do 2D kinematics. So even though these examples are kind of simple, I want you to make sure to go through this process so that when we get to the harder problems, you have internalized the process and you can use it for those. Okay, first example. All my examples involve cars. First example, a car has an acceleration of 3 meters per second squared. How long does it take for this car to go from 10 meters per second to 25 meters per second? So this might be the situation when you get on a freeway on-ramp. You enter the on-ramp at 10 meters per second, you push down on the gas pedal, the car accelerates, and you end up 25 meters per second driving on the freeway. How much time does that take you? Okay, so let's solve this problem using our problem-solving process. First, identify that it's a kinematics problem. I'm telling you right now it's kinematics. Second, identify the known quantities. So let's write down what we know. Let's say known quantities. Well, we know that the car's acceleration has a value of 3 meters per second squared. We are given the car's initial velocity, 10 meters per second. We're given the car's final velocity, 25. That's all the information we know. So now let's identify the unknown quantities, what we're trying to solve for. Well, the important unknown in this problem is the time. When we say how long does it take, that's another way of asking what is the time. So t is our unknown. So now let's select the appropriate equation to use. And the way you do this is you look at the quantities that you've listed and see which equation contains just those quantities. Now it looks like the first kinematic equation contains those four quantities: v final, v initial, a, and t. The second kinematic equation contains some stuff that we don't know anything about. It contains x final and x initial. We weren't given any information about those. And if you think back to algebra class, what we're really trying to do here is get as many equations as there are unknowns, because that's the only way you can solve for unknown quantities in algebra. It's having the same number of equations to use as you have unknowns you're looking for. So if we chose this one, we would have too many unknowns, not enough equations. The same is true for the third kinematic equation and the fourth kinematic equation. They both contain information we're not given, and the fourth one, in fact, doesn't even contain the quantity we're trying to solve for. So it's completely impossible to solve the fourth equation for time. So with all that said, it looks like the first equation is the one we want to use. So we'll use v final equals v initial plus at. And now we'll solve it. Solving usually involves a few steps of algebra, and what I want you to do, always in this class, is do the algebra first and put the numbers in at the end. So I'm keeping my equation in symbols for now. I'm going to do the algebra. Vf minus Vi equals At. T equals Vf minus Vi over A. Now I have an answer for t that depends on these symbols, and in fact, I've now solved the more generic problems where it doesn't, where this would work for any possible values of A and V initial and V final. Now I can plug in the particular values that I have for this problem, where V final was 25 meters per second, V initial was 10 meters per second, and A was 3 meters per second squared. So that's 15 divided by 3, which is 5. And notice the units, meters per second on top, meters per second squared on the bottom. They work out so that you get seconds, just like you would expect. So 5 seconds is how long it takes to complete that speeding up process, maybe as you're getting on the freeway. All right, I have 2 more examples. So I'm going to keep this stuff here. I'm going to erase the example I just did. Second example. A car traveling at 30 meters per second. That's freeway speed. Slams on the brakes. And comes to a stop. does it travel? All right, what's the braking distance of this car? Let's do our process. Step 1, identify that it's a kinematics problem. It is. Step 2, identify your known quantities. Okay, what are we given? We are given the initial velocity of 30 meters per second. This phrase, comes to a stop, is another way of saying the final velocity is 0. A lot of times in these problems, it won't say VF equals 0. It'll say the object comes to a stop. So you need to learn how to translate words into math. This will be an ongoing learning process throughout the semester, being able to turn words into equations. So when you come to a stop, that means your final velocity is 0. And this process takes 3 seconds, so that means that t equals 3 seconds. And now we identify our unknown. Problem says, how far does it travel? When you hear how far, you should think displacement. So our unknown is delta x, the distance traveled. And keep in mind that displacement means x final minus x initial. So in a situation like this, we might not know the actual location of x initial, and instead we just figure out how far the object has traveled. So let's select the appropriate equation, step 4. Keeping in mind that x final minus x initial is delta x, and so we might need to mentally substitute that in one of our equations. So we know v initial, v final, t, we're looking for delta x. This first kinematic equation is not going to do it. We don't know a, and this doesn't even contain x at all. Second kinematic equation. Well, it has v initial, v final, t, and if you subtract x initial from both sides, you get delta x on the left. So in fact, that second kinematic equation is going to work, because rewritten, it looks like this. Now the third kinematic equation, we could also put delta x on the left, but unfortunately that contains a, which we don't know. And the same is true of the last kinematic equation. We do have delta x over here, but we also have an a that is not part of the information we have. Too many unknowns in those equations. So we'll use the second one. There's just one unknown and the rest of the quantities we know. And notice that after I put x initial on the left side and rewrite that as delta x, I've now done all the algebra that I need. So solving it, I don't really have to do anything else. It's already written in the form that I need. So delta x is 1/2 V initial plus V final T. That's my general solution written symbolically, like you should always do it first. And now I can put in the values specific to this question. V initial was 30 meters per second. V final was 0. And the time is 3 seconds. So 1/2 of 30 is 15. 15 times 3 is 45. Meters per second times seconds is meters. So the car travels 45 meters, which is a pretty long distance. That's half the length of a football field or a soccer field. So if you're traveling at freeway speed and you slam on the brakes, you probably can't stop much quicker than a few seconds, and you're going to travel a long distance. So it's hard to avoid crashing into things when you're driving that fast. Let's do one more example. I'm sticking with the car for these examples. Don't worry, we will do all sorts of other situations not involving cars, but that's the simplest thing for now. Example 3, a car accelerates from rest at 4 meters per second squared for 5 seconds. How far does it travel? Let's do a process. Step 1, identify that it's a kinematics problem. It sure is. That's all we know how to do so far. Step 2, identify known quantities. First known quantity is written in words, not in numbers. It says the car starts from rest. That means that its initial velocity is 0. Next known quantity, acceleration is 4 meters per second squared. And the next one is time is 5 seconds. Now our unknown quantity that we're trying to solve for is how far. Remember, how far means displacement. So our unknown is delta x. So now we need to select the appropriate equation. Which one should we use? Let's go down the list. Equation 1, does that work? Not at all. That does not contain displacement. There's no way we could solve this to figure out what we're looking for. Equation 2. That does contain displacement. Remember, if you subtract x initial from both sides. But it involves v final, which we don't know. So there's too many unknowns. Equation 3. This also involves displacement. If you subtract x initial from both sides, it has v initial and t and a, and we know all those. So it looks like equation 3 will work. Equation 4 will not work because too many unknowns. It has displacement over here, and it has a v final, which we weren't given. So equation 3 is the one to use, x final equals x initial plus v initial t is 1/2 at squared. We do one tiny step of algebra. We subtract x initial from both sides, because that gives us delta x. And that's our general solution to the problem. We can now plug in the numbers we're given. V initial was 0, so this first term is 0. And we got 1/2 a 4 meters per second squared times t squared, 5 seconds, quantity squared. 1/2 of 4 is 2, 5 squared is 25, 2 times 25 is 50. Meters divided by second squared times second squared is meters. So this car travels 50 meters while undergoing this acceleration for 5 seconds. All right, so now we've seen several examples of the problem-solving process with the kinematic equations. These examples were on the simpler side of things. Some kinematics problems can get pretty complex, especially when they're two-dimensional, but we'll build up